right, class, so today we're going to cover Chapter 5. Chapter 5 is all about discrete probability distributions. So friendly reminder that in Chapter 2 we created frequency tables based on observed data, and we drew histograms for each of these frequency tables. Now what we're going to do is we're going to create tables and histograms for theoretical data, and these data are going to be numbers that are probabilities. We're going to be plotting the values for a random variable along our x-axis and the value for our probabilities on our vertical or y-axis. So let's get into talking about what a discrete random variable is. So a random variable is a variable that has a single numerical value for each outcome of a random procedure. So first of all, we know what a variable is from high school math and from earlier in this course. A variable, typically denoted with x, is a letter that can take on different values. For instance, sometimes in a math problem, x could be 0, sometimes it would be 2, it could even be like 5 or 6, right? So in this case, our discrete variables are going to take on integer values. So let's look at an example. So we're going to perform a procedure that can result in random outcomes. And what we're going to do is we're going to toss a coin 2 times and record the outcomes. So I could toss the coin and get 2 heads. I could toss the coin and get a heads and a tails. A tails and a heads, or 2 tails. So far we've just been looking at whether we got heads or tails, and there's nothing numeric about this. So what we're going to want to do is assign a number to our assumption. So let's focus right now on counting the number of heads that we got in our table to the right. So here I have 2 heads, here I have 1, here I have 1, and here I have 0 heads. So x is 2, 1, 1, and 0. So we've now assigned a random variable to our coin flipping problem. And it can only take on these 3 values, 2, 1, or 0. So far, for this problem, our random variable is x, and it can take on either the value of 2, 1, or 0. Recall what we said when a random variable has a single numerical value for each outcome of a random process. Flipping a coin is a random process. Let's look at another example. Suppose a medicine is developed to cure the flu, and this medicine is given to Joe, Jim, and John. Okay, I'm not very creative with picking out names, sorry. The procedure is observed from who gets well from taking the medicine. So we could have no one get well, just Joe, just John, just Jim, Joe and Jim, Joe and John, Jim and John, and Joe, Jim, and John. If you have any questions as how I got these possible incomes, try and think back to when we talked about all possible outcomes. Maybe you might have talked about some set theory before. So these are all the possible outcomes that we could have. So once again, no numerical outcomes. So we need to decide what we want to assign our random variable to. And I'm interested in counting the number of cures we could get from this table. So no one gets well would be 0. Joe gets well would be 1. Jim gets well would be 1. Same with John. And here I'd have 2 people get well, and if everyone got well, we'd have 3. So now I have a random variable x that can take on 4 different possible values. 0, 1, 2, or 3. So here we have a random variable assigned for our procedure. There are 2 types of random variables. This chapter focuses on discrete random variables, right? This is when we usually count items, such as number of heads in a coin toss, the number of hearts when drawing cards from a deck, the number of students who prefer chocolate to vanilla, cars of speeding intersection, and so on. We're going to focus on this type of variable in this chapter. Continuous random variables are usually used to measure items such as height, weight, temperatures, distances. Remember, discrete values can only take on whole number values. And continuous values could take on anything. I could have 0, 0.257, 1.02, right? And that's where discrete and continuous variables come from, which we talked about when we were talking about the different types of data being either qualitative or quantitative, discrete or continuous. So here are some probability distribution tables. These look like a frequency table, but instead of writing frequencies on our y-axis, we write the probability. Okay? So here I have the probability distribution of adding two dice. So if I roll two die, I add them together, what is their sum? So for example, the only way I could get a 2 by rolling two dice is rolling a 1 and a 1. There are two possible ways for me to get a sum of 3. That'd be rolling a 1 and a 2, or a 2 and a 1. In this case, order matters. And here's the probability distribution for that. So let's go back to our example 1. This is when we were flipping two coins. And remember, my random variable could take on one of three values, 0, 1, and 2. So we begun with this table. Now this P of X column is going to be filled with the probability of getting 0, 1, or 2 heads. Now the only way I could get 0 heads was 1 out of how many possible outcomes? 4. The only way I could get 1 head was 2 out of how many possible outcomes? 4. So we'll simplify that to a half. And then again, the only way I could get 2 was 1/4. So again, P of 0 is the probability we'd get 0 heads, 1 head, or 2 heads. So our final table with the distributions in it, like I'd calculated, here are the probabilities of each of these occurring. Let's take a look at the probability distribution. So here's our histogram. We've got our random variables along the x-axis, our probabilities along our y-axis. Oh, isn't it beautiful? So I've got 0, 1, 2. These numbers could have been a little better spread out. Sorry, guys. Notice that the height of each rectangle is the value of the probability. So here, probably getting 0 heads is 1/4, 1 head is a half, 2 heads is 1. Notice that this graph is also symmetric, right? It is evenly distributed. Some things to keep in mind are that each rectangle in the probability histogram has an area of the probability of the random variable. So for instance, on our previous slide, the rectangle over, we didn't look at 1 here. The rectangle over 1 head case had a width of 1 and a height of 1/2, making its area 1/2. So let's go back real quick and label the areas in here. So the areas of our table in this are 1/4, which is 0.24, 1/2, which is 0.50, and 1/4, which is 2.5. Remember, the probability of all possible outcomes occurring is 1. So here I have 0.25 plus 0.50 plus 0.25 equals 1. Notice this will always be true on a histogram. Okay, right, the probability must always be between 0 and 1. Let me erase my little... Okay. Notice in this next point, the probability must also be between 0 and 1. So if we ever compute a probability and it's something like 1.25, you know you made a mistake. And that the sum of all the probabilities in a table must be 1. So if you add them all up and get a probability less than 1 or greater than 1, you also know you made a little mistake. And that could just be a tiny mathematical error. That's why it's always so important to check your work.